How can we realistically get under the ice on Europa? Why is Venus such an underappreciated destination for spacecraft? How big is the universe? And in Q&A Plus, are ion engines good for deep space travel? All this and more in this week's Question Show. It's time for the Question Show. Your questions, my answers, as always, wherever you are, across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Night family, if we were able to drill through the ice of Europa, wouldn't the pressure completely blast out any probe that we tried to send down? No. So imagine how this is going to work. You land your drill bot on the surface of Europa, and the lander deploys this thing that looks like a dart, like a torpedo. And on the front of this thing is a decaying chunk of plutonium that's very hot. And then the rest of the equipment and machinery is in behind this torpedo. And then it sits on the surface of Europa, and the front starts to melt, and then it starts to tilt down, and then it starts to melt down into the ice on Europa. And as it does this, it's reeling behind this wire that is, can be tens of kilometers long. As long as it's really small, it doesn't really matter. And then it melts down in the front of the probe, and then the water sort of percolates around behind it, and then it freezes behind it because it's still exposed, cold, right? It's surrounded by ice, it's exposed to space, it's very cold. The water's going to freeze. And so this melt probe is going to be trapped in this chunk of water as it's going down. And gravity is really just pulling it down into Europa. And it is balancing out the pressure around it. And the entire melt hole is completely frozen over, but has this wire in between so it can still communicate with the surface. After a couple of years, the melt probe finally reaches the bottom of the ice and the beginning of the ocean, but it is in exactly the same pressure as the ice that's all around it. And then it opens up the front of the melt probe and lets out these little submarines that can explore around and gather information and swim down to the bottom of the ocean and collect data about what's down there. Try to communicate with the European space whales and then send that data back up this wire back into space. Klondike 69 None. I don't get it. Why do you think Venus is such a good destination for sending spacecraft when the conditions there would destroy anything that we can build in minutes? Venus has been explored, but not well. So when you think about, say, the exploration that's going on at Mars, there are orbiters at Mars that have the resolution that they can see features on the surface of Mars that are about a meter across, right? We have pictures of the rovers from space seen by orbiters around Mars. But the resolution of the best images that have ever been taken of the surface of Venus are in the hundreds of meters. They're terrible, but they're the best we've got. And this was images that were taken by NASA's Magellan spacecraft back in 1990. And so we haven't had better images of the surface of Venus since 1990. But there are some new spacecraft that are in the works to go to Venus. There's the Da Vinci spacecraft, and there's the Veritas mission, and then the European Space Agency is doing its Envision mission. And so we're going to get a refresh on images of the surface of Venus, better radar scanning of the surface of Venus. And yes, we learned from the Soviets that as they attempted to deploy their spacecraft and landers down into Venus, that as you pass through the atmosphere, the temperatures increase, the pressures increase. Down at the surface, it's 90 times as much pressure as Earth's atmospheric pressure, that the temperature is more than 470 Celsius. I forget what it is, but it's hot enough to melt lead, hot enough to cook a pizza. Like really hot. And yes, it tore apart and destroyed those spacecraft within, less than an hour. The spacecraft were rendered non-functional by that. And the way they worked is that they were essentially a refrigerator. The spacecraft kept all of its electronics inside and had a pressure vessel that was attempting to keep the heat from Venus from getting inside to destroy the electronics. But eventually the heat got in and cooked everything, and the spacecraft was killed. But that's very old technology. There's a lot of really interesting work that's being done to advance our understanding of Venus and to come up with materials and technologies that would allow much better exploration of Venus. And so there's a couple of places for this. One is that NASA is working on electronics that can handle natively the temperatures that you see on the surface of Venus, that they developed high temperature electronics, computers, sensors, things that can just remain in this high temperature environment. And there's other practical applications for that kind of technology just on Earth. And you imagine, you have jet engines, you have fusion reactors, you have places that are very hot, and you still want to have your electronics function. And so they might not be as fast as the fastest chips that are coming out of Silicon Valley or out of Taiwan, but they're still going to be able to perform that kind of capability. And then there are mechanical ideas to be able to have like clockwork rovers that can operate down on the surface of Venus. And so there's a lot of really interesting ideas that would allow a rover that could go down to the surface of Venus and survive for months at a time. There's other technologies that haven't been tried out yet, like the idea of a Stirling engine, that you essentially allow the heat to get into your vehicle slowly. And as you do, you're putting that to work. You're sort of taking advantage of the difference in temperature between the outside of the rover and the inside of the rover. And then as that heat is trying to creep into your rover, you're putting that to work and using that to run your rover around on the surface of Venus. But once you get up to about 60 kilometers altitude on Venus, then the pressure is very similar to what we have here on Earth at sea level. The temperature is roughly the same as what you experience at sea level. And so the temperature and the pressure are good. And air, on Earth air, if you had the mix of oxygen and nitrogen that is the Earth, that is a lifting gas on Venus. And so you could have a dirigible, you could have a balloon that is filled with atmosphere from Earth or the equivalent thereof, and then that would just be a lifting gas on Venus. And so you could be in a habitat that is floating around on Venus. And so flying vehicles work very well on Venus. The Soviets tested out a couple of balloons very briefly when they were attempting their exploration of the surface of Venus. And it works, but the problem with like helium balloons is that the atmosphere escapes from them very quickly. So you need a way to be able to replenish the atmosphere in your balloon to keep it inflated. And there's some new ideas. There's an interview you're going to see very soon where they propose that you can actually pump carbon dioxide out of the atmosphere of Venus. You can split it into oxygen and carbon monoxide, and then those become a lifting gas in your balloon. And so you can constantly pump and replenish the balloon, and you've got this floating platform that can float around on Venus forever. And then you can imagine different versions of this. Like, the thing can descend down to the point where the temperatures are getting intolerable. You can deploy a tether down to maybe the tallest mountaintops on Venus. You can try to collect samples, bring them back up. So there's a lot of really interesting new technologies, new ideas, on and some fairly serious proposals on how you could collect samples. You could do sample return mission from Venus. So don't write the planet off. And when you think about it, like Venus is the closest example we have to Earth. It is the same size as Earth. It is the same mass as Earth, roughly. It has about the same surface gravity as Earth. It's made of the same stuff as Earth. And yet it went horribly wrong while Earth went awesomely right. Why? Well, what is it about Venus that's so different from Earth? Obviously, it's closer to the sun, has increased temperature. It's thought that maybe there was liquid water on the surface of Venus in the past. Was there life there? Could we see the kinds of ancient riverbeds, the things that we see on the surface of Mars? Could we see that on Venus? So there's a lot of really good reasons to explore Venus, and it is just chronically underexplored. And Venus is actually easier to get to than anywhere else in the solar system. It's relatively easy to send a spacecraft to Venus. It's about as hard to send a spacecraft to Venus as it is to send it to Mars. And we get more opportunities. Mars, we have to wait 2 years before we can send a mission to Mars. We get a much faster cadence in being able to send missions to Venus. So there's a lot of really good reasons for us to continue exploring Venus. People aren't as excited about Venus for the longest time because it looked like Mars was the place where the life was. That's where all of that attention and focus and budget was being expended. But now you're seeing the detection of gases like phosphine in the atmosphere of Venus. That could be a potential biosignature. Maybe there's life in the atmosphere of Venus. And also, as we we discover more and more exoplanets out there in the universe, we realize that Venus is the best example we have of an exoplanet. It's the one that we can do as a comparison, as a ground truth, right? We've got Earth, we've got Venus. Mars is just too small. It just doesn't count. Earth, Venus, and then we can compare those two worlds at everything that we're seeing that is roughly that size out there across the universe and use that to better understand what kinds of planets are out there. So Venus matters. It's time to shout out our new patrons at the $5 level and above. Goth 2000, L. Jones, Emanek, Robeck, Dennis Gregory, Tim Blank, Tristan Mulib, Fred Kadee, Lynn Johnson, and James Smith. Join our community at patreon.com/universe today. Aaron Perelmuter, size of the universe, observable or otherwise. So the observable universe is the universe that is possible for us to see. In other words, since the Big Bang, light has been traveling for 13.8 billion years, and that light is reaching us. And so you can imagine there is this sphere around us where the light has been traveling. Now, your instinct would say, well, that then the radius of the observable universe is 13.8 billion years, but it's not. The radius of the observable universe is actually 46.5 billion years. So the universe is 92 billion light years across. And that is because over the course of the 13.8 billion years that the universe has been around, the universe has been expanding significantly, that we have been moving, that distant places have been moving away from us. And when you add all that up together, you get this 92 billion light years across. So that is the size of the observable universe. But that is only the observable universe. How big is the actual universe? Well, the answer is that we don't know. And the way you would measure the size of the actual universe is kind of the way that you would measure the size of the actual planet Earth, which is that you would attempt to measure the curvature of the Earth. And then if you measured the curvature of the Earth, that would tell you if you then extrapolated that curvature of the Earth, that would tell you the size of the actual Earth. And so, we learned the size of the Earth before, zero, right? A couple hundred years of BCE, you had Eratosthenes, who did this amazing experiment where he put a pole that was in one location, I think Alexandria, and then at the exact same time in another location, they measured the size of the angle that the pole was casting. They had two different angles because these things were separated by, I think, like 100 kilometers. And then based on that, they were able to calculate the actual size of planet Earth. But if the shadow cast by the poles was exactly the same length, then that would tell you that either the Earth is so big that you can't measure the shape of the Earth, or the surface of the Earth is infinitely large. And this is the same conclusion that astronomers have with the size of the universe, which is that either, we can't measure the curvature of the universe, and therefore either the universe is whatever is the minimum size for it to appear that way. And that's like 1,000 times larger volume than the volume of the universe that we can see, or is infinite. And so, how big is the actual universe? It's at least 1,000 times bigger than the observable universe and is also possibly infinite. John Stanton, what is the shape of the universe? So we talked about the size of the universe. What is the shape of the universe? And the answer is, again, we don't know. But there's a couple of options, right? So the first option is that the universe is infinite. And if the universe is infinite, what does shape even mean, man? Because if everything goes on forever, what is the shape of something that is infinite? But if the universe is finite, then we can make some kind of guesses about that. And that's based on some of the fundamental properties of the universe that we understand. And that is that the universe is flat. And so when we say flat, we don't mean like it is flat, like as a pancake. What we mean is that parallel lines remain parallel forever. And so if you take two parallel lines and you fire them on Earth and they follow a longitude line on the Earth, they start out at the pole, they separate as they go down to the equator, and then they come back together. And so that is different from what happens in the universe, where parallel lines remain parallel forever. So the universe has to be flat. And so then there are specific topologies that match a flat universe, because you're going to have something that wraps. So if you fire your 2 laser beams in one direction, and they're going to go for billions of light years, and then they're going to wrap around the universe like a fancy game of asteroids, and they're going to come back to their starting place, and they'll still be parallel. And so if the universe had any kind of curvature to it, then the beams would separate from each other, or they would get closer together. And so there are 3-dimensional objects that would function like that. And so the classic example is a torus, a donut, that parallel lines remain parallel on the surface of a donut. Try it for yourself. You'll see that if you go around the top of the donut, if you go around the side of the donut, the parallel lines remain parallel. But a cube also works, right? You could have 2 parallel lines, they go along, they hit the corner of a cube, they go around the other side, they remain parallel, they keep going. Or a dodecahedron, right? Like a 20-sided die. So there's a bunch of these possible shapes, and there are countless shapes where the topology of the shape allows for parallel lines to remain parallel in a universe. And so we don't know the shape, but we can sort of understand the kind of topology that it has to have if it is finite. But if it's infinite, then all bets are off. What does shape even mean? Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call that Q&A Plus. And this week's bonus question, are ion engines good for deep space travel? I'll put a link in the show notes so you can watch that. All right, those were all the questions that we had. Thank you, everyone who asked your questions in the YouTube chat. Everybody who asked their questions during the live show, which we are on hiatus from our live shows until the end of August. So now I'm going to talk about how summer is going. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bradley Griffin, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, David Gilton, David Matz, Evan Pro, Greg Feely, Hudson Ward, James Clark, Jeremy Matter, Jim Burke, Jordan Young, Josh Schultz, Marcel Smets, Michael Purcell, Modzo, Paul Robach, Rank Kaidu, Robeck, Sean Sargent, Stephen Fallon Munley, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So as you know, we are on our summer hiatus, live stream hiatus right now. And so that means that I'm not doing the live show every Monday, as well as we're not doing Astronomy Cast, but I'm still doing all of my other work. And so I just wanted to let you know how summer is going, which is that it is very hot and very dry. And I've been spending a lot of time outside. And so I've got a couple of pictures that I want to share with you. So early in the morning, I go outside and sit and drink my coffee and work on my deck. And we've got a bunch of squirrels that are roaming around my garden. And so, and they just don't care about us at all. Very curious. And so here's a picture I took of one of the squirrels coming over and looking at me. You don't move and just hope they don't get mad. And then the other thing people have been asking about is my fence, which I've made a willow fence. And here's what it looks like during the day. And I've had no end of problems with deer getting through the fence. And this year, we had a few break-ins and they did eat a bunch of the fruit trees. But now I think I've got them under control, he says. And so here is one of the deer at night trying to make his way through the fence, and he just gave up and walked away. So summer's going well, doing lots of stuff outside, lots of hikes and lots of gardening and lumberjacking, and I'm having a good time, and I hope you are all as well. All right, we'll see you next time.